Assalamu alaikum, my dear students. Very warm welcome to our online chemistry class. Today we are going to discuss a very important topic from organic chemistry, that is isomerism. Isomerism, one of the vital content from organic chemistry, and every alternative year or every frequent year there is some questions from this content come in HSA. So it's a very important, and I hope you will all go along with me. Now in this class, what are the contents? The contents are types of isomerism, structural isomerism, stereoisomerism, geometrical isomerism, and optical isomerism. Today we will discuss only structural isomerism because it's a vast content and one class is not enough. So we will discuss only structural isomerism, and in next class we are gonna discuss rest of the topics. So let's move on to our class. Before starting our class, some topic or some terms need to be understand. That is, if we don't understand that, we wouldn't be able to understand the further topics. Like we need to know about the functional group, what we have discussed previously. We need to know about the bonding structure of carbon atom, what we have learned in first year syllabus in chapter bonding. And another thing is that how boiling point of different compound varies. And in today's class we will have some idea about it. So let's move on. First of all, we need to know what is isomerism. If we fragmentize this word isomerism, there are mainly two parts, iso and mer. Iso means same, and mer comes from Latin word merus, which means molecules. So literally isomer means same molecule. So what will be the definition of it? So isomer is that the compound which molecular formula are same, but their structural or three-dimensional arrangement are different. So they are called isomer of each other, and this phenomenon is known as isomerism. So what are the type of isomerism? Now we are going to discuss about the classification of isomerism. Isomerism mainly classified into two types, that is structural isomerism and stereoisomerism. In structural isomerism, it also classified into four types. Number one, chain isomer. Number two, positional isomer. Number three, functional group isomer. And number four, tautomerism. In positional isomerism, there is another term mentioned, is that metamerism. In some of the textbook, metamerism has been treated as a different topic, but the basic term is same. Both belongs to mainly positional isomerism. That is why I have kept them in a same point. And stereoisomerism are also two types. Number one, geometrical isomerism. It is also classified into two types, that is cis isomer and trans isomer. Another part of the stereoisomer is that optical isomerism, and it is also classified into two types, which is enantiomer and diastereoisomer. Before moving to our class elaborately, I would like to discuss the bottom line of this topic. What are that? That is, in structural isomer, the mainly structure will be different, but molecular formula will be same. But in case of stereoisomer, both molecular formula and structure will be same, but their three-dimensional arrangement will be different. In case of geometrical isomer, in carbon-carbon double bond, if the bond rotation is restricted, then geometrical isomer arises. And finally, optical isomer, it's light sensitive, and it occurs if chiral carbon present in a compound, and due to that it can rotate plane polarized light, what we are going to discuss later on elaborately. Now let's move on one by one. Before that, a little summary, that is, what are the structural isomers? It has mainly three parts: chain isomer, positional isomer, and functional group isomer. In chain isomerism, only length of carbon chain will be varied, but functional group will be same. In positional isomer, the position of functional group will be varied, but functional group will be same, as well as length of carbon chain, but in finally functional group will be different with same molecular formula. One thing need to focus here, that for both chain and positional isomer, their chemical characteristics will be same and they both have same functional group, but their physical characteristics will be differ a little. But in case of functional group isomer, both the chemical properties and physical properties will change, because functional group has been changed. And in first class we learned that the chemical character of an organic compound totally controlled by the functional group. Now we will discuss elaborately one by one all these terms. First of all, chain isomer. As I said previously, that is, in chain isomer the carbon chain length will vary. It arises due to different length of carbon chain, but their molecular formula will be same. Here one thing need to be remembered, that if branching increases, its boiling point decreases. So greater branching, lower the boiling point. Now let us see one example, that is C4H10. It is a molecular formula and it actually have two chain isomers. One possible structure is that a straight chain. In that straight chain there are 4 carbon atoms, and as we know that it is a normal butane and it has 4 carbon atoms in its main chain. And another possible structure is that 2-methyl propane, and here one of the methyl group has been shifted to middle of the carbon, and the main chain length there are 3 carbons. So for in first example there are 4 carbon in main chain, and in second example there are 3 carbon atoms in its main chain. So only difference is that the length of carbon chain, but their molecular formula are same. And let us see what are the different in physical characteristics. I have kept same example. Now for the N-butane, the boiling point is 0.5 degrees Celsius minus 0.5 degrees Celsius, and for 2-methyl propane the boiling point is minus 11.7 degrees Celsius. So as I said, if branching increases, boiling point decreases. So here there is one example. Now our second topic is that positional isomerism. In positional isomerism, the molecular formula will be same, but the position of functional group will be different. That is, within same molecular formula, same functional group, but position of functional group will vary. And here also their chemical characteristics will be same, but physical characteristics will differ a little. Now let us see one example, that is, in first compound it is pent 1-in. In pent 1-in, or that is we can say also pentene 1. In pentene 1 the double bond lies at the side of the carbon chain, at the beginning of the carbon chain, and in second example it is also pentene, but the double bond lies at the middle of the carbon. That is why we call this pent 2-in. So only difference is that the position of the double bond, otherwise the molecular formula or functional group are all the same. So it is one of the example of positional isomerism. Another example is that another example is that 1-chlorobutane and 2-chlorobutane. Here the green ball represent the chlorine atom. So if we see clearly, then we'll be able to see that the position of the chlorine has been different. In first compound, the position of chlorine at the first carbon; in second compound, the position of the chlorine at the second carbon. So it is example of positional isomerism. Here there are third example. In third structure, it is also 2-chlorobutane, because in naming we have learned that we need to number the carbon chain, and number should be started at the end from where functional group is nearer. So ultimately if we number from opposite end, chlorine comes with second carbon. So, ultimately second and third configuration is all the same. So, that should be, that is also named 2-chlorobutane, not 3-chlorobutane. So, we need to remember. Now, we will discuss about metamerism. What is metamerism? At the beginning of my class, I said that both metamerism and positional isomerism are quite similar, but what is the basic difference? It is applicable for ketone or ether, that is some divalent functional group, and in metamerism the number of carbon atom will vary in both side of the functional group. So, if we see one example, that is pentanone 2. In pentanone 2, CO is at the second carbon, and in pentanone 3, CO, that is keto group, is at the third carbon. Here both belongs to ketone, so they will have same chemical characteristics, but their physical properties is different a little, like the boiling point of pentanone 2, that is 39 degrees Celsius, and boiling point of pentanone 3 is 34.5 degrees Celsius. So, here if we follow these two structure, that is here functional group is CO, and in both side of the CO the number of carbon atom actually different. So, it is metamerism, and I said previously that it is also some example of extended version of the positional isomerism. Now, our next content is that functional group isomerism. In functional group isomerism, within the same molecular formula, there are different functional group could be possible. That is, within same molecular formula, completely different compound could be there. Here they will have same molecular formula and they will have different chemical characteristics, because functional group completely changes and chemical characteristics completely controlled by the functional group. Here their physical property will also be changed. Now, first example is that alcohol and ether. If there is alcohol, its another functional group could be possible within same molecular formula, that is ether. If there is aldehyde, another functional group isomer could be possible, that is ketone. And final example is that if there is carboxylic acid, the ester pattern could also be possible. So, let us see one by one this structure. So, first of all we will discuss about alcohol and ethers. Both belongs to they have same molecular formula, but in case of alcohol the functional group is OH, and in case of ether the functional group is O. So, one belongs to alcohol, another one belongs to ether. These are the general formula of them. Now, one thing we need to focus, in alcohol there is OH group and it is polar, and due to polarity it can form hydrogen bond with themselves or with the water, and due to that its boiling point is higher and it is highly soluble in water. But in case of ether, it cannot form hydrogen bond because oxygen atom lies between the carbon. That is why it is totally non-polar, quite non-polar, and it cannot form hydrogen bond with itself or with water molecules. So, it is insoluble in water, and the chemical character is that in case of alcohol they show variety of chemical characteristics, and they are generally Lewis bases because they contain one lone pair electron in its structure, and but ethers are quite inert, though they show little some of the chemical characteristics, but not vast reactions like alcohol. So, we can consider them as quite inert. Now, our next example is that aldehyde and ketone. As I said, if aldehyde is there, ketone structure also be possible. So, in aldehyde CHO functional group is there, and in ketone CO functional group is there. You can see the general formula of them. In case of both aldehyde and ketone, the main functional group is that CO, where it is polar due to dipole-dipole interaction. But in case of ketone, it contains two alkyl groups, and due to that its polarity decreases a little. That is why its dipole interaction is little lower than aldehydes, and due to that its physical properties varies as well as solubility. Now come to the chemical characteristics. As they have different functional group, so their chemical characteristics are different. Here aldehyde easily oxidize to acid, but ketone generally does not oxidize to acid, but at extreme condition they do oxidize to acid. So the oxidation of ketone quite difficult. Another thing is that aldehydes reduces to 1 degree alcohol, and ketone reduces to 2 degree alcohol. So these are the evidence that they do react differently. And our final example is that ester and acid. In acid it contains COOH, that is carboxylic group, and in ester it contains COOR functional group, and you can see the general formula of them. Just like alcohols, in acid they are also contain OH part, and due to that OH part it is polar and it can form hydrogen bond due to that polarity. So acids are highly soluble in water, and due to electronegativity of the oxygen atom it can easily loses proton. But in case of ester it is quite non-polar, because it contain at the side of the functional group there is alkyl group, and due to that it is quite non-polar, and mainly esters are the fat molecules, and we know fat molecules doesn't dissolve in water. And the chemical characteristics is that due to the polarity, oxygen atom can easily eliminate hydrogen as proton, so it is acidic and they show variety of chemical reactions. On the other hand, fatty acid generally unreactive, and if we hydrolyze them they actually converted to respective acids. So now our final content is that tautomerism. It's little interesting one. In case of tautomerism, compound with one functional group automatically it means by itself, we will not apply any external condition like temperature, pressure. One compound with one functional group automatically will rearrange by itself to another functional group, and this two pattern is known as tautomer of each other, and total incident is known as tautomerism. Here one example of tautomerism, it is the example of ketone. In ketone it contains carbon oxygen double bond, and in double bond there is a pi bond, and pi bond is weaker. As we know, oxygen is more electronegative, so it pulls the bonded electron towards it, and due to that oxygen atom get negatively charged and carbon atom get positively charged. To compensate that positive charge, what follow that red arrow at the display, to compensate that positively charge, it takes the bonded electron of carbon hydrogen from neighbor carbon atom, and ultimately the carbon atom get neutral and it eliminate proton, but protons are positive and oxygen atom is negative, and unlike charge attracts each other. So this proton again combines with that negative oxygen, and finally it convert to enol. So why we are calling this enol? Because it has been named enol because it contain a carbon-carbon double bond which is alkene, and from alkene it comes in, and it also contain a alcohol group, OH group, and due to alcohol group in functional group we have learned that alcohol is named by all. So that's why in final compound there are two functional groups, one is in and another one is all. That's why it has been named enol. So here is the explanation for that. What I just said, that due to more electronegativity oxygen pulls the bonded electron, so oxygen get negatively charged, carbon atom get positively charged. To compensate that positive charge, carbon takes the bonded electron of neighbor hydrogen and eliminate as proton, and finally this proton combines with the negative oxygen again and convert to enol. Here ketone automatically converting to enol, that's why it is known as ketoenol tautomerism. It was all about our today's class, and in next class we will discuss elaborately about the stereoisomerism. So what I would like to say that go through with these topics, go through with your textbook, and then learn all this, and hopefully next day we will come with a new topic. Till then, stay safe and goodbye.
The video and its content is subjected to copyright. Convention of this video elsewhere is a punishable offense. Any redistribution or reproduction of part or all of the contents in any form is prohibited. You may not issue or commercially exploit the content, nor you may transmit, duplicate, publicly display, or make derivatives of this video. The video is protected by intellectual property claims to stimulate and ensure originality. All rights reserved by Adamji Cantonment College.